Hello there and welcome to another video on module 1. We will be discussing microoperations in this lecture. So microoperations can be classified into three different types: the arithmetic, the logic, and the shift operations. Microoperations are basically elementary operations performed on data stored in registers. Registers exist in the CPU, and the data that is stored in the registers, we perform basic operations, and these operations are called microoperations. In the first case, arithmetic microoperations are performed, and these are, as the name states, arithmetic operations. So they're basically done on numeric data, and they include operations such as addition, subtraction, increment, decrement, and so on. Addition. So the addition microoperation is given by the following statement, where data from register 1 is added with the data from register 2, and it is then transferred and stored in register 3. And we have the subtraction microoperation, which is represented by R1 minus R2. So the data from R1 has data R2 subtracted from it, and then it is stored in R3. In actual circuit implementation, this is done by adding 2's complement. Since subtraction is the same as addition of 2's complement, we use the following notation, where R1 is added to the 2's complement of R2, which is the same as R1 minus R2. Increment, another microoperation. Increment is where we add 1 to the data value. So the data stored in R1 has 1 added to it, and then it is stored to R1 again. The decrement operation is where we subtract 1 from the data. So when R1 is stored in any data stored in R1, it has 1 subtracted from it, thus being a decrement operation. The increment and decrement operations are implemented by the use of binary up-down counter. So this is the circuit that is used for incrementing and decrementing. Binary adder. To implement the operation of addition, 4-bit binary adder is used. The 4-bit binary adder is implemented by using 4 full adders. The carry bit from each full adder is sent as the carry in for the next adder. We have two numbers, binary numbers A and B, and the first bit for A and B are given to the first full adder, the next 2 bits are given to the next one, and so on. The carry in is set as 0 or 1 based on the requirement, and our final binary sum is going to be derived from S0 to S3, with the carry bit being S4. To implement the operation of both addition and subtraction, so we could call this a general adder subtractor or a parallel adder subtractor, we make the use of XOR gates and the common M bit. So M is given as C in. Full adders are made the same way as in a normal adder, where the carry of the first one, carry out, goes as the carry in for the second one. The A bit in this case is the same, is given directly, while the B bit is XORed with the carry in, and then it is sent to the full adder. So the addition and subtraction operations can be combined into one common circuit by using the XOR gate with each full adder. With the help of a mode bit, we can add or subtract. So in case 1, when the M bit is 0, okay, the 0 XORed with B will give us B. Hence, it will be the sum S0. It will be the sum of A0 and B0, as we did in the general adder. M1, when M is 0, it performs basic addition. While in the case of M being 1, when we XOR B0 with 1, it will give us the complement of B. Hence, the sum of A0 plus B0, complement of B0 plus 1, is giving us 2's complement. The addition of 2's complement is also known as subtraction. Hence, M1 will be allowing us to perform subtraction. This is how the M bit can help us in doing both addition and subtraction using the same circuit. A 4-bit binary incrementer is implemented using 4 half adders. So we have the first half adder, where we give the A0 bit, A1 in the second, A2 and A3. The carry bit out of the first half adder is sent as into the second. The output of here is sent to the third, and so on. We get some outputs, and our input, the carry in, is used as 1 to increment the value. Hence A0 plus 1 gives us the increment of the 0th bit. Then we get the carry of 1. Depending on the carry that comes out from the sum, we use the carry and then add it to A1, giving us an incremented final answer. The increment can be determined from S0 to S3, and in case there is a carry bit, it can be determined from the C4. So the increment option does the task of adding 1 to the register data. It is done by using n half adders in a series of n bit incremental. So if we have an n bit number, we're going to have n half adders. Since we had 4 bits in the previous number, we used 4 half adders. Each half adder requires 1 input and 1 carry. In the first half adder, carry is fixed to 1. As we increment, okay, the carry is generated from the previous half adder, and then it will be carried forward via carry input. Final result is available from S0 to S3 lines. A 4-bit arithmetic circuit can perform micro operations collectively, and they can be done using just one circuit. The following is the truth table for arithmetic operations. When we have select lines S0 and S1 using following inputs, and then we have the carry bit. The input we give at Y along with the selection lines and the carry bit is going to give us the output as follows. And the micro operations that can be performed are given in the table. We have add with carry, subtract with borrow, subtract, transfer A, increment A, decrement A, and transfer A again. Based on these combinations, all these operations can be performed depending on the inputs. Here is the implementation of the arithmetic circuit for performing all the arithmetic operations in one single circuit. We use multiplexers and full adders. Our selection lines and carry in are given from here. The selection lines are given to the multiplexer, and the carry in goes to our full adder. A0 as always given directly to the full adder, while the B bit is sent to the mux in different combinations of either 1 or 0, and it is also given along with direct 0 digits or 1 digits based on the required output. We can derive this entire circuit using the truth table as explained in previous lectures. The 4-bit arithmetic circuit is having the following working. So when we do addition, if we need to do addition, then the select lines have to be 0, 0. The value of B is applied to the Y inputs of the adder. Thus, if Cin is 0, the output will be A plus B, while if Cin is 1, the output will be A plus B plus 1. Both cases perform addition micro operation. It's either without carry or with carry. In case of subtraction, we have the selection lines as 0, 1, which will be allowing us to get the value of B0, since we used a NOT gate for B over there, and it is applied to the Y inputs of the adder. When Cn is 0, the output is A plus B dash, which is subtract with borrow, while when C1 is 1, the output is A plus B bar plus 1, which is 2's complement, hence known as subtraction, basic subtraction, and does not have any borrow. In terms of increment or transfer, when we have selection lines as in the form of 1, 0, the 0 is applied to the Y inputs of the adder, hence D equals to A plus 0 plus Cn. If Cn is 0, the output is transfer because A is directly transferred when Cn is 0. If Cn is 1, then A plus 1 takes place, hence it is an increment operation. Decrement and transfer, when our select lines give the input of 1, 1, then 1 is applied to the Y inputs. Thus we have D equals A plus 1 plus Cn. When Cn is 0, we have D equals A plus 1, 1, 1, 1, which is decrement, and we have 1, 1, 1, 1 because it is 2's complement of 0, 0, 0, 1. When A plus 1 is done, we have 2's complement of 1 taken here, and accordingly it helps in decrement. If Cin is 1, then the output is the 2's complement plus just 1 from C. Cin becomes 1, and when we have the 2's complement subtraction and addition, it gives us the cancelling out, and hence it increments A. Next step is the logic micro operations. These are binary logical operations that are performed on data. Here are the following binary operations that can be performed, such as clear, ANDing, transfer, XORing, ORing, NOR, and it is done on the data stored in the following registers. If we discuss one stage of the logic circuit, we can see that if we have two selection lanes and a multiplexer for inputs A, B, okay. So for performing the AND operation, we can have selection line set to 0, 0. Thus, it will give us the ANDing of A, which will come out as the output F. If we need to do ORing of A, we can use the selection lines 0 and 1, which will help us in getting the OR value. The XOR will be gotten when we have selection lines as 1, 0, and finally at 1, 1 we get complement of A since we're giving NOT gate. So this is one stage of a logic circuit, and multiple stages can be implemented based on the required logic functions. Logic micro operations can be used for the manipulation of individual bits. Okay, so if we have a number, we can change the bits as required by using logic micro operations. So we consider that we have data register A, okay, and data in B. So the register B is used to manipulate the bits in register A. We have these manipulation tasks that can be done: selective set, selective complement, selective clear, mask, clear, delete. Mask is also known as delete, and then we have clear, insert, and compare. We'll be discussing them further on. Selective set. Selective set is basically the operation where the pattern in B is used to set certain bits in A. So if a bit in B is set to 1, then the same position in A gets set to 1. If B is 0, then A has its previous value, the same value as it initially had. This means that we are performing the OR micro operation for selecting and setting the bits. So if we have the initial number A as 1, 0, 0, 0, 1, 1, and then we have B set to 0, 1, 0, 1, 0, 0. So the second and the fourth bit is set to 1. This means due to the OR operation between 0 and 1, the output will be 1. Hence, we are able to selectively set certain bits in A to 1, and this is done using the OR micro operation. Then we have selective complement. In selective complement, the pattern in B is used to complement certain bits in A. So if B is set to 1, then the position in A gets complemented from its original value. Otherwise, it remains unchanged. So this uses the XOR micro operation. And for example, we have an initial A, and then the first bit and the second last bit in B is set. So what this does is it complements A. Since A is 1 at this point and it is 1 at this point as well, it will become 0. The complement of 1 is 0 in terms of A. Hence, it shows the use of XOR micro operation for selectively complementing certain bits in a given register or data. Selective clear helps us to clear it is a clear operation basically, and the bit pattern in B is used to clear certain bits in A. So if we have a register A with some data and we need to clear certain bits, we need to make them 0, then we can use a pattern B, and whichever bit is 1 in B will clear the same bit to 0 in A. So if we have the first and third bit as 1, then the first bit in A and the third bit in A will be set to 0. This is clearing. We are not setting them, but we are clearing the data from there. It's basically deletion or erasing of data in those certain spots. The mask function, also known as delete function, is the one where the pattern in B is used to clear certain bits in A. Okay. If a bit in B is set to 0, the same position in A gets set to 0. Okay. Otherwise, the bit in A keeps its previous value. So over here we can see that when B is set to 0, A gets set to 0 as well. So in these positions B is 0 and hence A becomes 0. Only where B is 1 is the position at which A is transferred in the same manner. This uses the AND micro operation. It is the reverse of clear. So what happens is in clear we use 1 to remove the bit, but in this case the 0 is the one that removes the bit. Clear or compare. In this operation, if the bits in the same position of A and B are the same, okay, they are cleared in A, or else they are set in A. Okay, so this basically compares the data in A and B, and it produces all zero result if they both are equal. Hence, if A has 1 in the first bit and B is also 1, then it is set to 0. Okay, they both are 0 initially, so it's already 0. When they are not the same, then A is set as it is, but again when they are similar bits, then it is set to 0. Insert. The insert operation is used to introduce a specific bit pattern in A. So if we have to change the pattern in A, okay, then we use the insert operation. This is done by in two steps. First we mask, okay. First we perform the mask operation. So we clear the desired bit, okay, where we need to set the certain bits, and then using the OR operation we insert the desired bits. We can see that in the following example. If the original A is as follows and we need to change the original one to this form, you can see that all the parts are same except for the last part. The last 4 bits are different. So what we are going to do is first we're going to mask the last 4 bits. The last 4 bits are going to be deleted and they'll be made 0, and we're using 1 over here, okay, just as in masking. The zeros will clear the digits, while the ones are gonna give the same output of A as it was initially. Once we've cleared them, we can use ORing and give the new bits that will be added to A. So when we give an OR operation, what happens is wherever it's 0, the zeros are going to come as they are. Wherever it's 1, the ORing is going to be done between 0 and 1. It has to be either one of them 1, so the 1 will be transferred as it is. Same thing here, 0 bits are there, but the 1s will be transferred as they are. Hence we finally get to the desired output. Thank you, and see you in another video.